Hi everyone, in this video we will learn about double integral in polar coordinates and some applications of that. Let's start by looking at something we have already seen. When we have a double integral of this form, what we do is a process of what you can think of as partial integration, which is first we evaluate this first integral with respect to y, where we treat x squared as a constant. So the integration of x squared would be x squared y, with the limits being 1 to 2, and the integration of y raised to negative 2 would be y raised to negative 1 over negative 1 via power rule, and going from 1 to 2, which will give us a constant. Right, so that's just this particular integral. And what does that come out to? It comes out to x squared 2 minus 1, which is 1, minus 1 over y, so 1 over 2 minus 1 over 1. So this comes out to x squared plus half minus 1 is negative half, negative negative becomes a positive. And as you can see, this is now a function of x, which makes sense because our next integral goes from negative 1 to 3 of x squared plus 1 half and is with respect to x. So there's a dx. So this becomes an x cubed over 3 plus an x over 2, both of which go from negative 3 to 1 and negative 3 to 1. Putting in the limits, this becomes 1/3. 1 cubed is 1. Subtract negative 3 cubed is negative 27 plus a 1 half, 1 minus negative 3. You get a 1/3, 28 plus 2, which when you take the LCM, combine them up, you will get a 34 over 3. Then the next thing that we have seen is sometimes when you have functions like double integral of sine y squared dy dx, now here we run into trouble because finding the antiderivative of sine y squared is not easy. Well, actually it's not possible. However, if we do a dx dy, then we are able to work with it. And so what we will do here is we will do a change of order. So change of order, and that's going to change things up a little bit. So what's happening right now is we're going from y equals x, because we have y first. So y equals x to y equals 1. So we are traveling in this direction. And when we change the order, we will now travel in the horizontal direction and look at the value of x. So in terms of dx, when we have sine y squared, where does x start? X starts from x equals 0. And it goes to x equals y, which is this line. And in this region, what happens to y? Y varies from 0 to 1. And when we do this, now we are able to solve this because the first integration is now with respect to x, and that's going to give us a y sine y squared dy from 0 to 1, which is solvable because we can use a u substitution of u equals y squared to get du is 2y dy, or y dy is 1/2 du. We've already seen an example like this, so I am kind of doing it faster. So this becomes 1/2 sine u du, which becomes a 1/2 negative cosine u from 0 to 1, which is a negative half cosine 1, minus cosine 0, which is 1. So here, in order to solve this particular integral, you have to do a change of order. Okay, now let's move on to polar coordinates. Again, polar coordinates are something that you have seen prior. It's another way of representing a point on the two-dimensional plane. What we do is we take a circle. Any point x comma y can be thought of as a point on a circle, which is at of a radius r, and at an inclination of theta, which is your angle from the positive x-axis. So what we are doing is we're saying we can call this point x comma y. We can also call this point r comma theta. And there are some easy relations you can form between these three quantities. The first comes from Pythagoras theorem, is that r squared equals x squared plus y squared, because this is exactly the length of x and this is exactly the length of y. The other come to us from trigonometry. So you have cosine theta, SOHCAHTOA, so adjacent, which is x over r, gives us x is equals r cosine theta, and sine theta, which is opposite over adjacent, gives y over r, which gives y is r sine theta. So if you ever forget which one is cosine, which one is sine, you can just use trigonometry. There are other relations. For example, using tan theta, you get SOHCAHTOA, opposite over adjacent. So you get a value for theta, which is inverse tan or arctan of y over x. And this is called the polar coordinate. Polar coordinates are very useful when we have things that have circular symmetry. So we will be using it quite often in this course. Now, when we work with polar coordinates, the way we segment when working with a double integral is slightly different. We don't have regular rectangles. Instead of regular rectangles, we have what are called polar rectangles. So for example, this shaded rectangle here, the radius varies from some value to another value. Sorry, that's the angle that varies from one value to another, and the radius. So this would be your change in angle, so delta theta, and this is your change in r, delta r. And we're gonna work with these rectangles instead of your regular rectangles as you know them. So if f is continuous on a polar rectangle, which is we just saw polar rectangle is defined by a range of radius from r equals a to r equals b, and a range of theta from alpha to beta, where beta minus alpha is between 0 and 2 pi. This is to avoid overlapping. This is to avoid overlapping, multiple rotation. Then the double integral of f of x comma y over the region R can be written as a repeated integral by converting f, rewriting it in the parametric form of r cosine theta, r sine theta, and getting an r dr d theta. So slightly different here, we will see why. We usually had dx dy, but here now we don't have only dr d theta, we have r dr d theta. Why the extra r? So in rectangular coordinate, this is how this was working. Whereas in polar coordinate, when you look at the area of this thing, this area is given by r. So you have dr, which is the change in length here, and this is your change in theta. But if you remember, when you have theta and a radius r, then this arc length, the formula for arc length is r times theta. So while the change in angle is d theta, this particular change is r times d theta. So the area of each of the shaded rectangle is r dr d theta or r d theta dr, which is why we get that additional r. Let's look at an example in order to understand what's really going on. So evaluate this double integral where r is the region in the upper half plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. So now we don't have a rectangular region, right? We have a general region, and we could put this into a rectangle and work with it, but it's not going to be as easy, because as you can see, solving for y or x requires you to use square roots. So you would have y is square root of 1 minus x squared and all of that stuff going on. So instead of that, we will use polar coordinate. So we have, it's the upper half of the plane bounded by, so we have one upper half, so we just need half a circle. That's the half circle for, so this is the region we are working with here. That's the region between the upper half of the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. So this radius or this distance is 1 and this distance is 2. All right, so what does it say? Our result says that as long as there's nothing overlapping, fxy dx dy becomes, in the polar coordinate, I rewrite it as r cosine theta, r sine theta, and r dr d theta. So the first step we are going to do is we're going to rewrite this function as given. So 3x becomes 3 cosine theta plus 4y squared becomes 4r squared. Oh, sorry, I missed an r here. 3r cosine theta plus 4r squared sine squared theta, and an r dr d theta. Radius goes from 1 to 2, and theta, since it's a half circle, goes from angle 0 to pi. Multiplying that r in there, we get 0 to pi, 1 to 2, 3r squared cosine theta plus 4r cubed sine squared theta dr d theta. Now at this point, it's the same story, which is we can work with them separately. So when we evaluate the dr first, we will treat each of the theta terms as constant. So we have 0 to pi, all this thing happening, which we will deal with later, and the derivative and the integral with respect to r is going to give me 3r cubed over 3 cosine theta remaining as it is, the limits being 1 to 2, and 4r to the 4 over 4 sine squared again remaining as it is with the limits 1 to 2. The 3's cancel, 4's cancel, so I actually have a 0 to pi. 2 cube is 8 minus 1 is 7. I get 7 cosine theta. 2 to the 4 is 16 minus 1 is 15. 15 sine squared theta d theta. Now this splits into 2. 0 to pi, 7 cosine theta d theta is straightforward, and 0 to pi, 15 sine squared theta d theta. This is an integral that you can work with using the half angle formula. Now this is going to be, the double angle formula, or same thing. This is, so evaluating the integral of sine square and cosine square is something you will face quite often. So what you want to use here is this identity. Cosine 2 theta is 1 minus 2 sine squared theta, so that sine squared theta is 1 minus cosine 2 theta over 2. Now this is a straightforward integral. This is 7 sine theta from 0 to pi. Sine pi is 0, sine 0 is 0, so this is 0. Whereas this will become 15 over 2 integral 0 to pi, it shouldn't be 15, 1 minus cosine 2 theta d theta. So the first part becomes 15 over 2 theta from 0 to pi minus integral of cosine theta is sine 2 theta over 2, again 0 to pi, and this is again 0 because sine of even multiples of pi is 0. So you just end up with 15 pi over 2. So that's something that you will get. Okay, here's a problem that you can try. Evaluate x plus y dA, where R is a region in the first quadrant bounded by the circles x squared plus y squared equals 4 and x squared plus y squared equals 9. So I will assign this as an extra credit problem. And remember, all extra credit problems are to be submitted via email, which means do this work, take a picture of it, send me the picture. So you need to show both picture and the answer, right? So not just the solution. All right, I'm going to end this video here. We will continue with this topic in a following video for this. Thanks, everyone.